let's talk about metaprogramming. So this panel session will be composed of a few short presentations and a discussion, and I hope you, the audience, will participate in this discussion. So the goal is to talk all together about what do we want as metaprogramming tools for ML. The participants to this, so I will be the moderator of this discussion. The participants will be Thomas Petricek from Cambridge, Nicolas Pouillard from Copenhagen, Jeremy Yallop, and Hongbo Zhang. So I'm asking them to come here in front of the audience. Let's get them together. So the objective is to understand what tools and techniques we have and we want to manipulate and extend the syntax of ML. And here we will restrain ourselves to syntactic tools. So we won't speak about runtime generation and runtime code generation and stuff like that, like MetaOCaml, for instance. So the tools we'll be talking about will be Camel P4 from the OCaml system, but also other tools from F# and Haskell, which we may not know very well if we are OCaml programmers, for instance, and the other way around. So this is the order of the small presentations that I'm proposing. First, Thomas will tell us about metaprogramming tools in F#. Then Hongbo will tell us about Camel P4 and so what it is and maybe what you would like it to be. Jeremy will tell you about the two Camel P4s. And Nicolas will tell us a few words about what's available in Haskell. Okay? So I think at any time of the presentation, and of course afterwards, you will be welcome to interrupt and say, hey, I don't understand this, or this is what I would like, and so on. So let's try to do something interactive right from the beginning. Okay, Thomas. Let me retrieve your slides. Fine.
Good, thank you. Yeah, so this is not any official F# statement. It's just my interpretation of what's happening in F#. And so I was observing the F# language, and my design principle inference algorithm told me that I think one of the goals that F# has is to really keep the language simple, because it's I guess an attempt to make it more accessible to a wider audience. So one of the ideas is that we probably don't want to extend the syntax. And the problem with that, I think, is that when people come to a larger team, they'll have to learn not just the programming language, but also all the specific syntactic extensions. And it's sort of one possible burden to having bigger teams using the project. But and that's probably one of the topics we can discuss, because I'm sure not everybody will agree. But at the same time, the F# syntax is already quite rich, so we can reuse it in some ways. I'll say a few things about that. And the other principle, I guess, is this arbitrary 80-20 rule. The numbers are just random, but the idea is, well, we want to cover the most common use cases and have some nice language support for that. If you don't want to do something beyond, then that might be quite difficult in F# compared to other languages. So one use case is to write some code that works with data, and that's sort of thing that you could solve with metaprogramming. In F#, this is solved with type providers that I talked about earlier. So that's one use case, possibly for metaprogramming that's covered by some F# technology. The other use case is, oh no, I switched it. So the type provider mechanism, that's when you want to access external data sources, right? That's when you have some data already, you just want to generate code for using that. The other use case is if you want to use your F# or ML style language to write code for, to run as SQL or as JavaScript, sort of cross-compile the language. So these two areas are areas that I guess the F# team thinks are important and that they have some mechanism for. When we were discussing this panel, one of the questions was what are the kinds of metaprogramming, how to classify it. And so my idea about this is that there's sort of 4 different options. What's the input and what's the output of the metaprogram or program. And the red bit is when we have input some code. So you can look at the program, do some metaprogramming, and then produce in the red bit data from looking at your code. The green bit is when you take some code, source code, and produce some more code, different code, that's going to be compiled as part of your program. The blue bit is when you have some input, some data, like external data source, and you produce some code for programming against that data source. And the violet bit, that's just when you have normal program that takes data. So that's takes data, produces data. That's not where metaprogramming happens. But in the remaining 3, in F# when you look at the blue bit, there we take data, produce code. That's kind of what type providers do. They do it in a more integrated way, but it's one area of metaprogramming. The red bit, when we take some code and generate data, that's what happens in F#, where you can take a look at some piece of F# code and translate it, for example, to JavaScript or to SQL. And that's another area where F# does something for metaprogramming. But there's nothing in the green bit where you can take code and use metaprogramming to generate different code and then compile that. So that's an area that's not covered in F#. And that's probably where you can do some really powerful tricks, but maybe that's also the area where you can get into difficult situations and produce, allow the user to write things that will be quite difficult to deal with. So the bit code from data, that's where type providers come in, and the bit data from code, that has been actually presented at the ML workshop some time ago. But there, the idea is that you can mark some method or function, and this is just an example from one web application that translates to JavaScript. So the code is marked with this reflective definition, and this just represents some update loop running in a web browser that waits half a second, then downloads the current state and refreshes the screen. But the idea is if you mark it explicitly with some quotation mechanism, then you can use metaprogramming to translate that to JavaScript, and you'll get some nice application for drawing. But yeah, so I guess in summary, the idea in F# is that it tries to pick the sweet spots where you need some metaprogramming, and I guess the 2 cases are when you have some code generated depending on data, that's the type provider mechanism, and the other is when you generate some data or some other language source code from F#.
Okay. Thank you, Thomas. The next presentation will be by Hongo Zhang. I hope my pronunciation is correct. Again. Okay.
Good afternoon. I am the second year PhD student in the University of Pennsylvania. Before I begin my presentation, I want to say before I became an OCaml programmer, I have been programming in communities for a long time, and I turned into the OCaml programmer. I enjoy every benefit, like the faster code, the type check. But one thing I miss is the meta-programming. So that's my topic today. First, we should give 3 examples of the power of macros. One is the syntax extension. Actually, syntax extension appears in the concept compiler in the Syntactic directory, and I will show you the file ELF parser is written using the bit stream syntax extension, and the code with the syntax extension is just 100 lines of code. And if we expand the code and see the vanilla OCaml code is 2,000 lines of code, and very unreadable. The second example is I derived the code generator for the source tree in the OCaml's compiler. This is one example is the type tree. It's in the typing directory. I show you the it's too big. Where is yeah. Yeah, it derived all the pretty printer with the pattern and the comparison and all the normal operation for the very big ASP and tens of thousands of lines of code. I mean, you cannot do it by hand. It's very big ASP. You cannot write those codes by hand. Actually, I do all the stuff for the. If you can go back.
No, you simply close it.
Okay. I mean, I derived all the code for the typing directory and parsing directory. It's more than tens of thousands of lines of code. And it's very tedious to write those code. And you cannot write it correctly. Very hard to write it correctly because the business pattern and then very tedious. Another example is my branch of CAM4. I branched the CAM4, and CAM4 it was written in 2 directories, 2 styles. One is the original syntax, the other is the revised syntax with syntax extension. And you see, we use the revised syntax with the syntax extension to save 50,000 lines of code. I mean, it really saves a lot of typing. And yeah. Another story is about the COS. COS is a communist object system. I mean, communist is a very old language. It was popular before the object-oriented paradigm became popular. So in the 1980s, the OO programming is very, very popular, and this community want to have those object layer. And they actually did. They designed a very expressive OO layer. It even supports the multiple dispatch, which doesn't appear in OCaml. OCaml only supports the single dispatch. And they did it. They don't extend the compiler, they extend using the list macros. And using the list macros plus the read macro. And they have a very class book called the Art of Meta Object Protocol. So I want to say the macros is the ultimate tool for the abstraction. I mean, even for language like Haskell is a very text language, but it's still a lot of syntax construct that's not first class. So you cannot save the boilerplate code by the more advanced type system. Because even when you introduce the get, you have to handle the general programming for get. And if you introduce the kind polymorphism, you have to handle the general programming for the kind polymorphism. And it's an endless war. So macros itself is programs. You can write macros which generate macros. I mean, so you solve all the problems. That's my point. So I will give a high-level overview of the CAM4. CAM4 is a very long-term software project. Its name is Preprocessor Preprinter. That's the name P4 came from. Preprocessor means you can customize the front end. And preprinter means you can also customize the backend. So, and it's composable. You can write in the Prolog syntax and have a C backend where it can before. So this is an example of how you train the parser. The first example is you use the original OCaml syntax and the output is the revised syntax. And the second example is you use the revised syntax and have an original syntax. We will go overview of the main features on CAM4. The first feature of CAM4 is it has a dynamical extendable parser. Means when you have a parser, you can extend without touching the parser. So you see the first one is a grammar for the arithmetic expressions. And then we want to extend for multiplication. Then we want, without touching the original source, we just extend. The second is the bit string syntax extension. The bit match is not a built-in struct in the OCaml. And we can extend the OCaml syntax with a bit match and have a special pattern. You see the first pattern is the 8-bit. Pattern match the 8-bit. And it's a value and then the 24 bits for the ELF format. It's very convenient for the bit string handle. And it will be compiled to the OCaml expression and linked to the C runtime. So it's very efficient actually. And this is another syntaxing example is by the JSP S expression lib library. And it's when the syntax see the with S expression, we try to trigger the type code generation for the list type definition. And we will I have designed a more modular type generation hook. We'll see it later. This is okay. Another main feature for the syntax extension is CAM4 support the generic delimited syntax extension mechanism. I mean, CAM4 the lexer support when you see the code. You can customize your lexer and pass it inside the code. This is very useful for the delimited syntax extension. We'll give the first example is cross quotation. Cross quotation is one special example of the delimited syntax extension. The cross quotation. So what is quotation? Quotation means you want to denote the abstract syntax using the concrete syntax. So you want to manipulate the abstract syntax, but it's very verbose and very tedious. And I'm very familiar with the concrete syntax. So I still want to use the concrete syntax to manipulate the abstract syntax. So think about we want to construct an AST node for the program. Actually, we have to write this way. I mean, you can. It's not a human work, right? It's too big. I mean, so the quotation mechanism means you just need to write the code the code and say it's a structure item. Now all is done. So how it happens means the cross quotation, the code inside the code share the same parser with the code outside the code. But the code outside the code will be passed to normal AST, and the code inside the code will be passed to a normal AST. Then it will be compiled to another AST which encodes the AST. So it's a meta operation. We have quotation and we also need a cross quotation. Suppose because we can't know all the AST in advance, we want to abstract over the code. This example, we can abstract over the code. The make big definition says we have make it big. You can anticode the dollar, the double dollar is anticode. So you can anticode interpolate the small AST and make a big AST. Cross quotation is fundamental to the meta programming because it is a very easy way to construct the code. And it's the only way to do the meta program because when you want to write macros which generate macros, the complexity will grow very dramatically and it's impossible to write by hand. We've already called the a very simple AST node test. And you can never, it's impossible to write by hand and correctly, in a correct way, right? And the cross quotation also shine when combined with the pattern matching. ML is very good. And have a very fancy feature is pattern match compared with the common list. And the code position can appear in the pattern position. And you can pattern match the code and do the code transformation. The delimited syntax extension is very general. You can not only cross-code the code, you can also customize your arbitrary lexer and parser. For example, you can customize your regex expression this way. You only need to define your lexer and parser for your own language. And the delimited syntax extension, the benefit is they will not conflict with the other parser. Another feature I think is very important, but I think I only have 15 minutes. I will not go deep. Is bootstrapable. Come before is so far as I know. Come before is the only macro system which is bootstrapable by itself. Come before is written in come before. I mean, like other macro systems like the Meta Haskell, Meta Ocamo, Template Haskell, they are all right in their original syntax. Come before is bootstrapped by itself. So the benefit here is very obvious because I grew the macro system. I introduced a new DSL, and I can absorb this language into my macro system. I can use this macro system, use this new language to write the next version of the come before. And that's the most useful feature, I think, in my opinion. Another is the come before doesn't require very much support from the compiler. Come before only need to see the SC definition of the compiler's definition. It's a standalone program. Okay, so after I discuss the main feature of come before, I want something is done very good in come before, but something is done not that good. I want to provide my opinions about how to improve the existing come before. We already know the come before now is a bit not that good. I mean, it's a bit messy and not well maintained. Yeah, I will go from the three aspects. So currently the come before doesn't, the lexer is hard coded. You cannot extend your lexer. I mean, this is very annoying. I want, actually it's done in my branch on come before. I mean, you can extend your lexer because sometimes you want to write in a very close way to write you want to customize the lexer. And when you postpone the C code, it's very annoying. The double arrow is a C operator, C++ operator, and you have to escape it. So one proposition is we should have an extensible and programmable lexer. The second is we should have an extensible and programmable and also functional parser. Currently the come before parser is an imperative. The imperative means when you mutate the parser, you cannot go back. This is a very bad idea because syntax extension is inherently conflict with other syntax extension. When I design my syntax extension, and if you design your syntax extension, and syntax extension is a global value, everybody can mutate it, and you want to limit the scope to be as minimal as possible. So we should have a functional parser. The idea of a functional parser is when I got out of scope, I should restore the previous parser. And the other feature is because the latest Ocamo release has exported the compiler as a library, is a very, very useful feature. Traditionally, we can only manipulate the syntax. Now, it's no longer true because we have the compiler as a library. Actually, I linked the Ocamo's compiler into the preprocessor. And we will see later we have a lot of things to do. The first, I want to say we should have a much more flexible parser. The grammar in come before, the existing grammar in come before is a syntax extension, but it's not first class. So my proposition is we should have a first class grammar. The grammar should be normal algebraic data type, but with a very convenient syntax extension. So we can customize our own embedding DSL to describe grammar. And it's actually just when we expand the code, it's just a normal algebraic data type. Then we can program the grammar. So we see the grammar is very large in the OCaml distribution. Like I remember in the Yak OCaml path tree is like 2,000 lines of code, and in the COM4 is I think the same order, 1,000 lines of code. And actually, we can program parser. If we program the parser, the parser will be very succinct. And the grammar should also be separate from the action, because when you define the grammar, you can derive it automatically without binding to the action. Binding the grammar, fix the grammar to the action is a very bad idea. Because I have designed grammar, and I fix the grammar to the action, the other people cannot reuse your grammar. Right? Because you have fixed the action, and other people also customize their action. And traditionally, we want to reuse other people's grammar, we have to copy-paste and to mutate the grammar to reflect our changes. This is a very bad idea. I mean, we should separate the grammar from the action. And we can use other people's grammar, just leak the other people's library. Yes. So this is the idea of the meta DSL, which is a DSL. We should design DSL to force the other DSLs. As we know, DSL is very important nowadays. But making a DSL is a non-trivial work. So what should we do if we want to design DSL? First, we define our algebraic data type. Then we can use our previous the first class grammar to write the parser in a very easy way. Then we derive the preprinter, because you have the grammar as the algebraic data type. You have all the information, and you can derive the preprinter automatically. And this is also done in the Sugar Haskell. And also we should derive like a visit pattern I showed you before. I mean, for a large ASD, it's a non-trivial work to write by yourself. And also we should add other type hooks. As long as we have many type hooks, we can derive more and more hooks, code generator. And it's also very easy to support the type operations. I mean, open entity in a syntactic way, because when we have the definition of the entity, it's a very easy way to add another branch. And now we have a compiler as a library. Even we don't have the source, we can type in and get a source. We can still derive the type operations. This is a meta program I already done in my branch. Let me show you. It's a bit complex. Let me show you how it works. So the first language is eval. Eval is because I link the OCaml compiler to the preprocessor, so you can eval the AST. So the first language eval will eval the AST at the preprocess time. The second language is a func_config. It's a meta program, which is a macro which generates macros to extract COM4 to generate the derived EQ automatically. So you will have several properties. The first is name, and the second is extract, and the most important is three, the set, compose. It tells me if I have AST node, what should I do? I should compose the AST node with the AND operation. And the default means the default branch is false. Prefix, because the COM4 is a syntactic meta programming. So you have a name, you have a type T, you will derive the function as EQ_T. Right? So when at the proper time, the COM4 can evolve the instructions. And then I have a plugin named EQ, will help me to derive the EQ code for the type definition. And the next language is derivative. The derivative is a very minimal language. It shows the first derivative is long, means it says the default quotation is OCaml. And keybar means I will keep the type definition, because when you derive the code, you can either keep the type definition or drop the type definition. And the third derivative is show code. It means I can download the code at the preprocessing time for debugging. And the fourth is a plugin add, means I will trigger the plugin at the proper same time. And the last is a default language called OCaml, and you will derive the code. So this is a very modular way to derive the code, because every syntax extension is delimited. Every syntax extension is delimited, and you can add the plugins as many as you want. It's a composable and a safe way. Okay, so now we want to go to the benefit of what we have the compiler as a library. So this is the data flow of the come before. The solid line is what is already done in the come before, and the dotted line is not done, but should be done in the future come before. We see because we have the compiler as a library. Traditionally you have string input, and we pass by the come before to the intermediate AST, and then either you will dump to the OCaml compiler pass-through, and then feed to the compiler, or just pre-print to the vanilla OCaml code and feed to the OCaml compiler. But we now have the compiler library. We have the pass-through. When we have a pass-through, we just go on to typing this pass-through, and then we have type true. And we already have the visitor pattern for the type true. Then we can transversal the type true. And if the OCaml compiler accepts the type true, we can just pipeline the type true to the OCaml compiler. If the OCaml compiler doesn't, we can just untype back to the pass-through and feed the pass-through to the OCaml compiler. So we have type definition. We can type in the environment. It's a very useful feature. For example, traditionally when you want to derive code for a tab-level phrase, you want to add a debugging information for the parameter. It's not doable because you don't have type information for the tab-level phrase. Now, because you can type in the pass-through, you have type information, so you can run your code like format.fprintf. And you have type information, you can inject the code. And as I said before, and you can even eval the AST to eval the AST, right? So unlike the traditional come before, you have to separate your syntax extension from the source code. You need to first compile the syntax extension, and then use the syntax extension to pre-process the file. But now you don't need that, because you can just eval your syntax extension. And on the fly, you get the syntax extension to derive the code. Yeah, so we have the OCaml compiler, we have type tree transversal for free. We have combine time evaluation also is for free. And we have non-intrusive code generation. Because we have the OCaml compiler, you can just read it from the .cmi file, the signature file, from the OCaml the interface file. And we can deserialize the interface file, and we get the pass-through type sheet definition, and we have pass-through, and we have derived code. This is very important for the deployment because other people don't want to touch the source tree. I can still derive the code, even without touching the source tree. So,
we should conclude now.
Okay. Yeah. So yeah, so because come before is a bootstrapable, so I think we can do more and more and make come before more and more expressive type macro system. Thanks.
Okay, thank you. So we understand that F# wants to keep it simple. Jeremy Alert now will duplicate camel before.
Yeah, so camel before is actually two tools masquerading as a single system, both very useful, but serving essentially different needs. So the first tool is a kind of labour-saving device, akin to a sort of electric screwdriver or a wheelbarrow or something like that. Not especially glamorous, but tremendously useful. It saves us from having to do some boring work which needs to be done. I'm talking about, of course, the type of code generation that we've seen examples of already, and that many of us are familiar with. The second tool that we find in Camel P4 isn't exactly a labour-saving device, it's more aspirational than that. It's something that helps us to think beautiful thoughts, something that enriches the soul, lifts up our thoughts to a higher plane. Not so much a wheelbarrow as a paintbrush or a violin. The thing about wheelbarrows is their behaviour is fairly predictable. I mean, you put your rocks or whatever in, you wheel it along, you tip it out, it's fairly straightforward. If you've ever tried to play a violin, not an accomplished player, you might find that the results will be a little more surprising, perhaps. Starts off okay, and then a sudden sound that's not quite what you hoped for. So the aim of what I'm going to talk about today is how we might make the violin a bit more like a wheelbarrow. Let's move on. Okay, so seen examples of this already. Camel P4 as a code generator. This is probably familiar to most people who've used OCaml. We have a type definition with an annotation following, which asks a Camel P4 extension to generate some code which will turn our trees into S expressions and back the other way. And when we run the extension on that input, then we'll get something like this for the function of one direction. A couple of things about this function. So the structure of it is quite predictable. It follows exactly the structure of the type definition, a branch for each constructor, a function call for each sub-value. We could have written it ourselves, but we're very happy that we didn't have to. We've used our wheelbarrow, we've saved ourselves some labour. Everything's great. Okay, another thing we might notice is that there's very little care taken in the generated code with respect to bindings. So if you look at the name v1, that's bound several times in the output, and that's absolutely fine. We're generating closed code. We don't have to care about the context in which we're generating this code. There's no danger of name capture. But the code generation procedure is quite straightforward and predictable, and we're very unlikely to end up with a nasty error message from when we come to actually compile the code. So the last remark on this example is that the actual syntax, we're thinking of using Camel P4 to extend the syntax of the language, but actually the syntax we've used, the with SX annotation on the type, it doesn't matter very much. The actual choice is irrelevant. We could have prefixed the type definition with something, or we could have written a separate declaration. The syntax here isn't the important thing. It's the labour-saving code generation that is the point. Right. Let's look at a second example where the syntax is the entire point. So this is a snippet of code from Chris Akasaki's dissertation about purely functional data structures. And I'm very happy with this piece of code. I like it a lot. I'm not going to talk so much about what it does, but just about the appearance. I think it's particularly elegant and really beautiful piece of code. So, starting at the top, the first thing we might notice is the type signature. So we've got the right type written here. It's a universally quantified type. The function is polymorphic, and we make use of that when we call the function recursively. We call it in a polymorphic recursive way. And so the type signature is an essential component here. The second thing I'd like to note is the lazy keyword, which occurs both in the pattern here and in the expression on the right-hand side. There's a very pleasing symmetry about that. We're taking apart a lazy value, and we use lazy keyword to do that. And then we write something essentially the same to put together a lazy value on the other side. There are also a few other little syntactic conveniences. We have abbreviated record patterns.
Does the lazy keyword, when it's in a pattern, mean that some computation gets delayed, or does that mean that the lazy value that's there gets evaluated?
The latter. It means it forces the lazy value. Yes, this is taking apart an existing lazy value. Yeah.
It's like co-lazy.
So, in today's OCaml, we can write this, which is wonderful. Just as it is, you can give this to the OCaml compiler, and it will compile successfully and run. Until fairly recently, that wasn't the case. The only way that you could write code like this was to use CAML P4 and to extend the syntax to support these nice features. We wind the clock back a little way. We can still write the function. We don't have to do some sort of strange global transformation. It doesn't look so nice now. This is, I don't remember the exact versions, but if we go back a few OCaml versions, and this is how we might write this polymorphic recursive function that operates on lazy values. So I've used an object here to support the polymorphic recursion. This allows us to assign a universal type. And when we call the function recursively, we now do so through the reference to the object. So we have self hash cons here. The lazy pattern has gone, and we have an explicit force on the right-hand side. The code's become a little less declarative, a little more imperative. We say now force this, build a lazy value. It's okay, but it's not a beautiful violin sound for me anymore, at least. Okay, so
does it do the same thing? Now that the force is under the lazy?
It does, yes, it does. Is that true? No, it doesn't do quite the same thing, actually. Strictly to be the same, the force ought to be pulled out. Actually, the behaviour will be quite different. Good catch. Yeah. Okay, so if this is actually the advantage that I claim it is, if by extending the syntax of the language, we can write code that's more pleasing, more beautiful, more of an aesthetic delight, then why don't people really do this? I mean, without any evidence at all, I'm going to claim that the the code generation tool in OCaml is used fairly widely, but this sort of syntax extension is not really popular. People don't really like to do this, and I'd like to spend a couple of moments to consider why that might be. So, of course, there are two people, two programmers involved in a CAML P4 extension. There's the person who writes it and the person who uses it. And of course, the person who writes it has to come first. It's actually more difficult than it might be to write an extension to the syntax of a CAML. So if you consider the lazy patterns extension and think about the code that's generated, you can see that you'll have to operate on the syntax itself. You have to transform the right-hand side to introduce these forces using a let, as I ought to have done before. And ultimately, you're going to have to write a capture-avoiding substitution. You have to introduce a temporary variable to hold the output of the force and then replace that.
Can you do it correctly if the lazy pattern is nested in some case, or I'm not really sure you can program this in the syntax extension.
I believe you can.
In some case, the question of whether you force or not may depend on you give some pattern files, and then inside the first one you might do another test and then decide which one. But okay, go on.
I'm pretty sure you can do it, but I'm not going to say how at the moment. We're going to talk about capture avoiding substitution, which is unfortunately more difficult than we might hope. A simple case, we want to transform the expression y plus 1 to replace y with x. everything's straightforward. Slightly more difficult case, we have a binding where y is rebound. Again, it's not particularly hard, it's a sort of elementary exercise. Oh dear. If we look at this slightly more complex expression, we have a problem, which is that we can't tell from inspecting the syntax of this expression whether y is free or not. So the external module may introduce y, in which case it's not safe to replace it with x. It would be entirely wrong. On the other hand, if the external module doesn't introduce y, then we are obliged to replace it with x. So we're stuck. We can't write a complete capture avoiding substitution that handles all cases. And this sort of thing makes writing syntax extensions a bit of a chore. You have to deal with these issues. I think this is one of the reasons why a lot of people might give up. At this point, you might say, well, I'm through with this. It's only going to make a minor change to my source programs. I don't care enough to write this. On the user's side of things, this sort of thing, if the user thinks about this sort of issue, or even if they're familiar with what's involved in writing the extension at all, it's going to introduce a feeling of unease. Did the author of this extension think about all these cases? What's going to happen if a variable is inadvertently captured? It's a justifiable feeling of unhappiness at having to think about the code generation process. Of course, if there are error messages, they're likely to be obscure and likely to require inspecting the generated code. It's not a happy business, and it's not ultimately worth the value that you gain from having a more beautiful syntax, at least in my experience, and I think that's a view that's widely shared in the community. Okay, so how might things be better? Well, fortunately we don't have to look very far from home to see a more successful syntax extension mechanism, which somewhat ironically is implemented using camel p4. If you go on the camel mailing list and you say, I'm a new OCaml programmer, I'd like to do such and such, I'm thinking of writing an extension to the syntax, I think you might be gently discouraged from doing so. I don't get the feeling that things are the same over on Club. I think if you were to say, here's my module, I've written this notation, is that okay? Yeah, I think people are generally happier with that. It's more in the culture that writing syntax extensions, writing notation is a normal thing to do. In fact, it's so much in the culture that if you dive into the sources, you'll find in the actual implementation of COC and the standard modules, you'll find this notation mechanism used extensively. So much for the culture. There's also a closer integration in COC with the tools of language. You can, while using an interactive COC session, you can say, where does this symbol come from? Which extensions define this? You can, you can interrogate the system. You can expand some notation to see what it expands to in your interactive session. It's all very closely integrated. And finally, and perhaps most importantly, the COC notation mechanism is integrated deeply into the language. So it's aware of bindings, it's aware of scopes. You can have a local notation that's only active in a particular scope. You can have notations that are mutually recursive with your other definitions. It's a fundamental part of the language rather than